Hello again. Remember last time we talked about going over the optical isomerism and stereoisomerism. So today that's what we're going to be covering as simply as we can in this video today. So to begin with, here we have stereoisomerism and the simple definition up here. Stereoisomers are molecules with the same structural formula but different 3D arrangements of atoms in space. Now the important thing to note here is the same structural formula and different 3D arrangements of atoms in space. You'll see what this really means by the end of the video for sure. To begin with, we have three types. We have enantiomers, diastereomers, and epimers. And these all have different meanings, which we'll see in a minute. So here we have an example of a stereoisomer, which, as you can see, when we have the definition of the same molecular formula but different arrangement in space. In this view, we call this Fischer projection, which I'll write down for you here. This is Fischer projection, which is essentially the 2D representation that we can see up here. We also have 3D, which you might see sometimes in my video, which we call the Howarth projection. Anyway, so here we have, if you count, 3 carbons, here, here, and here. So basically, as we can see, the 3 carbons on this side and 3 carbons on this side. If you count the hydrogens as well, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same number of hydrogens, same number of carbons, and of course, same number of oxygens as well. So in both cases, we have C3H6O3. And therefore, that means we can clearly see a different arrangement of atoms, but obviously the same molecular formula, which is here. And this is what we call a stereoisomer. And as if you remembered from my previous videos, this glyceraldehyde is an aldotriose. Triose meaning the 3 carbons that we saw here, and aldo meaning it's the aldehyde end, which is this here. And we also have a dihydroxyacetone, which is a keto triose. So this is the key difference here, the keto and the aldo, which is changing the arrangement in space. Again, triose, 3 carbons. Keto comes from this carbonyl group here, a ketone. So beginning with type 1, we have what we call enantiomers. The definition here is quite simple, non-superimposable mirror images. Now what that looks like is just down here below. Where we have D-galactose and L-glucose. You'll find out very soon what the D and the L means in D-glucose and L-glucose. But if I were to draw a mirror down the centre here between D-glucose and L-glucose, as you can see here, we're going to call this our mirror. As you can see in the definition, we have mirror images. So essentially, if you have a look at both molecules, we have the reflection of each atom on each side. That's our mirror image, which is non-superimposable. And essentially, where we get the D and L from is here. So we look at the final chiral carbon, and our chiral carbon I will define now. It's going to be the 4 different groups bonded around a carbon. So here you can clearly see this is the chiral carbon here, and it's bonded to this group, this group, this group, and this group. And clearly these are all different groups. 4 different groups bonded around a carbon is a chiral carbon. And we look to the last chiral carbon chain, so this one here, and this one here. And we look at this one, and as you can see, the OH group is what we're looking for, or the hydroxyl group. Here is on the right, and here is on the left. Now what that means is if it's on the right, we put a D here, and if it's on the left, we put an L here. It's simple to remember, just remember that left gives you an L, and the right, just happens to give you a D. Perfect, I hope that makes sense for you, keeping it simple so far. Now we're going to move on to a different type of stereoisomer. So here we have diastereomers. Now it's getting a little bit more tricky now. This is a non-superimposable, non-mirror image that differs at one or more chiral carbon centers. Now the key thing to see here is it's non-superimposable, non-mirror image. That's the main difference between diastereoisomers and enantiomers. The enantiomers were mirror images, however we cannot draw a mirror down the center here this time, because the chiral carbons differ at one or more. So as you can see in D-mannose and D-galactose, the carbons are differing here. You can see they're flipped. They're the same here and here. They're flipped again here. And the same here and here. So we have two differing chiral carbons, making this a diastereoisomer. Hopefully that makes it super simple, super clear. The main thing to remember, again, is a non-mirror image, so we can't just draw a mirror down the middle like that. We cannot do that. Instead, we look to see if they differ at one or more chiral centers. Now, type 3 is called epimers. Now, these are still diastereoisomers that we've just seen. However, they differ at only one chiral center. Now, you will see that just here with D-mannose and D-glucose. So if you look at our Fisher projections, we have the only difference here is a chiral carbon number 1 or carbon 2 in the chain. The rest are all the same, as you can see. So it only differs at carbon 2, or in other words, the first chiral carbon here. That's what makes it an epimer. So remember, it's a diastereoisomer again, but it only differs at one chiral center. Now for the best bit of the video that you all wanted to find out about is the optical isomerism, and we're going to make it as clear and simple as we can. So here we go with optical isomerism. Now the definition here is enantiomers which form due to asymmetric chiral carbons. Now we've seen chiral carbons before, remember, is this here. It's 4 different groups bonded to a chiral carbon. Now this is the final chiral carbon, which is the second last carbon in the chain of L-glucose. And L-glucose, remember, because we have the hydroxyl group on the left. So this here is L-glucose. And as you can see, we have 4 different groups. One here, one here, one here, and one here. Remember, R is just the rest of the chain, so all our hydroxyl groups and everything else in the chain. Now, this is a chiral carbon, as we said here, and this is what we call asymmetry, and this allows us to obtain D and L, like we mentioned previously. And the interesting thing that we get in optical isomerism is the diversion of plane polarized light when we shine it through the molecule. So the way we test for an optical isomer is exactly this here. Its ability to rotate plane polarized light in opposite directions. This is a key definition we need to know. Very, very key. And basically what this means is if we were to shine light, let's pick yellow for this, makes sense. And we say this is light coming through here. when this light goes to this molecule, it can come out here or it can come out here. This is obviously right, this is obviously left. Now, if it comes out to the left, we call this levorotatory. And if it comes out to the right, let's draw another arrow here. We're going to call this dextrorotatory. Now, again, the way I like to remember this is, again, levo, the L here is for left, remember, light going to the left, and then the other one, dextro, just means it's going to the right. And if we have levorotatory in an optical isomer, we're going to give it a negative. And if you don't understand, this just means negative. And with dextrorotatory, we're going to give it a positive symbol, so like this. Now what this means is we can have, again, with L-glucose, we can have L positive glucose, and we can have L negative glucose. And the same works for D-glucose as well. So this would mean that when you shine plain polarized light through this molecule, we get right dextrorotation, and here we get left levorotation. That's everything for today's video. Hopefully that's really simple, really well explained. If there is anything you didn't understand in the video or something else you want me to do in another video, please put it down in the comments, and as usual, subscribe, like the video, and turn on the notifications. Thank you very much.